Okay, so on Monday, we started talking about semiconductor materials. And we watched a video that showed that a lot of semiconductors are made of silicon. This is a base unit, but we could dope that silicon, as in inject other things besides silicon into that, that can make it behave in certain ways. And when we doped them, we could end up with what would be called a P-type material or an N-type material. So our P-type material are doped with a higher valence electron atom. So how many valence electrons did silicon have? 4, right? So that made it, again, why it's kind of a semiconductor. When you have 4 and you're trying to get to 8, you're not too close to 8 and you're not too close to 0, so you kind of stay there in the middle. But if anything, that is a super strong force to make you move those electrons into a conduction electron or something that can move, and then you might do that. But otherwise, you kind of stay in this covalent sharing of your 4 electrons with neighboring atoms. So what had more electrons than 4? So what got us an atom that had 5 electrons, but otherwise would be very similar in size to silicon? So you remember from the video what atom that was. Phosphorus, yeah, so phosphorus is right next to silicon on our atomic chart, or atomic table, but it has 5 valence electrons, and so it has a 5th one that doesn't fit well in its crystal lattice structure, so sharing 4 with its neighbors. So that 5th one doesn't have anyone to share with, and so it makes it really easy for oh, sorry, and I did this backwards. We did P-type, we'll do that lower. This is actually N-type. Sorry. N-type is doped with higher valence electrons, so kind of like extra electron. Higher valence. And that would be our phosphorus. What had a lower valence electron than silicon? So silicon had 4. I'm looking for one that had 3. That was boron. Okay, so boron made our P-type materials. Phosphorus made our N-type materials. It's called N-type because, again, with that extra valence electron, it's like I have a negative charge that can move. Okay, so hence a negative charge type. With a P-type material, it's called P-type because boron only has 3 electrons. Therefore, it has a hole where it would like another space to share with its neighbors covalently. So it's like that hole is the absence of an electron or it's a positive charge. We can arrange these semiconductor materials with P-types and N-type regions, again, based on what atoms we dope our silicon with, adding more phosphorus or adding more boron to them, in 2 general forms. So one form is called a diode, and that's where we just have a single area of a P-type material and then a single area of an N-type material from them. So again, our P-type will be doped with boron, our N-type will be doped with phosphorus if our base is silicon from that. So diodes have 2 material areas, one N-doped and one P-doped. The one we saw in the video, though, was a more complex form than just our diode version of that. We have 3 regions of doping. So we have, for example, here N-doping, P-doping in blue, and then N-doping again. And those 3 regions, along with what they're attached to, and we'll talk about those, make up what's a transistor, or a FET, which is a field effect transistor. And they had 3 doping areas that were different, N-doped, P-doped, and N-doped. You can have the same thing in reverse here, so this is my transistor here. I could have p-doped here, n-doped for most of the body of it, and then p-doped again here. So what was the difference between our n-doped and p-doped materials? Do we think A, our n-doped materials were had atoms added to our crystal structure with a lower valence number than our base material, while p-doped materials have atoms added to our crystal structure with a higher valence, or the reverse? N-doped had a higher valence number and p-doped had a lower valence number. B, right? So we just said that the n-dope, really like negative, means I have a higher valence number or an extra electron from that. When it's p-doped, I'm missing an electron, I have a lower valence number from that. When those regions hit each other, though, or where the p-doped interacts with the n-doped material, we get what's called the depletion region, because something's magical is going to happen with those charges from the p-doped region to the n-doped region when they're in close contact with each other. This would happen in my transistor as well, and any interaction between my n and p-doped where they intersect each other, I will get depletion regions. What's going to happen in that depletion region? So in that, when we saw with our N-type material, it has a higher valence electron. So again, it had like an electron that wants to move. Where is it going to move to? Yeah, it's going to move from the N-type to the P-type, but it won't move far. It will move right in this depletion region. So if that electron moves over here, I get an extra negative charge on that side. Okay. And in the P-type, really that was like they were holes. They've now got filled with an electron. What happens at the depletion region then, where these electrons move from, on my N-type material? What charge am I left with there? Positive charge, because I lost an electron from that. So all of these, make them red so we can see that maybe. All of these in the depletion region ended up positive, because the electron moved from my N-type material, but right where it's close to it, over to here. And if I lose that electron, I've now lost a negative charge or made it more positively charged. Okay, so we saw our N-doped materials had a lower valence number than our base material. Again, silicon has 4, phosphorus has 5, boron. Oh, nope, I did this backwards. Our N-doped materials have a higher valence number. Our P-doped materials have a lower valence number. So it makes our N-doped materials have an extra electron that isn't attached to our crystal lattice and can freely move. In that depletion zone, it will move. Our P-doped materials have an extra hole that should fill the lattice with an electron, since it's missing an extra valence electron. And so an electron will move into that hole from it. What are the charges of our N-doped material outside of that depletion zone? So not counting that area right next to where it's going to hit a P-doped material. Is my N-doped material negatively charged, positively charged, or neutral? You can talk to your neighbors, see what you think. I'm going to ask everyone to vote in a minute. Okay, so how many people say our N-doped material is going to be negatively charged? Okay, how many people say it's going to be positively charged? Okay, how many people say it's going to be neutral? And a lot of people didn't vote. Okay, but I got the most hands for neutral. Why is it neutral? Yeah, so again, when I N-dope it, all that meant is I added a phosphorus atom, right? And while phosphorus has 5 valence electrons, and silicon only had 4, how many protons does phosphorus have? The positively charged things in the center of their nucleus. How many would it have? 5. So is it a charged molecule itself? No, it's neutral. We only call it N-dope because it's like it has an extra charge compared to that valence structure to move, but it is not itself charged. So it's a really common misconception, and people will try to think that N-dope means negatively charged or that your negative charge left and then that's positive. That only happens when my charges will move in a very close area where they interact. And again, that's my depletion zone. Outside of that, I'm just left with plain old phosphorus atoms. And while this poor guy doesn't get a neighbor to bond with, compared to my Si atom here, gets nice bonding for this one. And I'd have another silicon atom over here that bonds this guy. And another silicon atom over here that bonds this one. And then one that bonds here. This guy has no friend to bond with, so he wants to move, and that makes him a good conductor of electric current from it. But he is not himself negatively charged, because where that extra electron is, there's also a proton inside that. So outside of my depletion zone, I am neutral. This is also true for my N-doped and my P-doped material. Right, so my P-dope just meant I doped with something with one less valence electron compared to silicon, so boron, which had 3, but it also only has 3 protons, so it's a neutral atom that I'm adding to it. It isn't itself charged. The only places I get charges are in this depletion zone where these two areas are going to interact, where they're close enough to draw electrons from one side to the other. So my phosphorus here again had 5 protons. It also has 5 electrons, and it is neutrally charged compared to my silicon. My boron had 3 protons and 3 electrons, and it is also neutral. What about in my depletion zone? So if my diode is the basic material where I just get 2 regions, and it's di, I get 1 p-doped and 1 n-doped, I get one nice depletion region right where they meet. Kind of like the demilitarized zone from North Korea to South Korea, right? We've got our enemy neighbors here, and they make a little peaceful zone in the middle. What's going to happen with charges in that zone? So where that n-doped and p-doped are very close to each other. So do we think A, our positive charges will build up in the p-doped material, negative charges will build up in the n-doped material? Or B, negative charges will build up in the p-doped material, positive charges will build up in the n-doped material? Or C, no charges will be created in the depletion zone as the materials are neutral? Talk to your neighbor, see what you think. Okay, I'm going to ask you to vote again. I want everybody to vote. We're going to start from the bottom this time to mix things up. So how many people say C? No charges will be created in my depletion zone because my materials are neutral. Okay, a few. How many people say B? Negative charges build up on the p-doped, positive charges on my N. Okay, a few more. How many people say A? Oh, we got about an even split between A and B. So with my N-type material, what was the difference in my valence? Did I have an extra electron or was I missing an electron? Extra, right? So it had like these electrons here that although they're not negatively charged compared to the number of protons, they don't fit in my valence structure. They don't have friends to bond with. So they're like free agents, and where are they going to go to? I'm not good with sport analogies. That's as close as I get. Where are they going to go from my n-doped material? Where are those electrons going to go? They're going to go over to the p-doped material. Okay? Why do they want to go to the p-doped material? To get, for instance, to fill a hole, right? They had a spot. They had a job there, right? They had a position on the team that they could be a team player, right? They had other things they could bond with to fill the hole like the boron was missing. So that means my p-doped material, right at that depletion zone, right where it was next to the N, now accumulated all these negative charges. Why is it negatively charged, not neutral? Right, so remember this was boron, right? I don't have my pen. And when boron only had 3, it was missing 1 here in its valence electron. So I moved my electron from my n-doped material to fill that here, but now I have 4 electrons, but boron only had 3 protons. So that does make it actually negatively charged. What does that leave the charge on my n-type material? At my depletion zone. So at right next to that p-tope. If those electrons left, what charge is there now? Positive, because again, nothing happened to those protons in those atoms. They aren't so free to move. But phosphorus over here, which had 5, now lost 1 of its electrons because it moved to here, right? But it still had 5 protons. So that makes it more positively charged than it was before when it was neutral. So my correct answer is negative charges build up on my p-doped, which sounds weird, right? We think of P positive, but again, it's not actually positive charge. It's what charges move. It's like my positive charges are going to move to the other side. My positive charges are then going to move to where my n-doped material was. They were talking in the video about holes moving versus electrons moving. Again, in theory, a hole doesn't really move. It just gets filled and then it's left a hole where its place is. The only thing that's really moving is my electrons, and that's the flow of electric current. Okay, so that's my diode. When I have those 2 junctions, P and n-doped, I again get a depletion zone buildup here. I'll get negative charges on the P, positive charges left on the N. It will only happen for a little tiny region where they're next to each other, because I don't have enough of a draw to pull, let's say, electrons all the way from over here all the way over there. Right? They're only going to move a certain distance from that, so I only get a little region from it. Another reason that I don't get them all pulled over here to there is that now I have an actual negative charge built here. Like charges repel, right? So if I try to move more electrons through this when this is actually negatively charged, they don't want to move through that. They would repel each other backward from it. So it only happens at a little area from it. So my p-doped material will become negative charge in my depletion zone, and the absence of electrons in my n-doped material makes my n-doped material positively charged. That makes my diode. That's simple when I'll have 2 interactions. The same thing's going to happen when I get 3 regions in a transistor. So again, n-doped, p-doped, n-doped, or you could have p, n, p. The order of that doesn't particularly matter except for how you design the rest of it. But I need 3 areas from them. 2 of them are going to be the same doping, 1's different. How that transistor works is, again, anywhere they interact, I'm going to get a depletion zone build up, where I get positive charges on the n-type, negative charges on the p-type will build up there. And normally, again, those charges are going to repel further electrical current through that. So if I have then on my p-type negative charges build up right here, then I don't want to send an electron from here all the way through from my source to my drain, connections to these transistors, because when it hits this negative charge wall, it's going to repel and send it backwards. Okay, so it prevents current from flowing in its default state. The only way I get current to flow all the way from my source to my drain, You can again think of a source or a drain like a sink faucet, right? So one's my faucet, one's the drain. How do I get current to go from one to the other? Is when I apply a small control voltage. Oops. Well, that was annoying. There we go. Voltage is applied to my gate. So in addition to a source and a drain, which I'm trying to get current to flow from this wire through my transistor to here, I have a third connection on my transistors. Slightly more complicated than my diodes. And that connection is called the gate. And I can apply some voltage to this gate that will help with this depletion layer. So if the body of my material is p-doped, then we just said that our depletion layer in the p-doped region will build up negative charges. What would I need to apply? What sign of voltage would I need to apply to my gate to get rid of negative charges? Positive, right? So if I apply decently sized positive voltage, then they're going to cancel out these negatives, and now current can flow all the way through it. But it'll only flow when I get that voltage applied. Again, you could have this in the NPN configuration, in which case I apply a positive charge because the body of my transistor, the main part of it is p-typed. What if I had the reverse and I had P at my source, doped P at my drain? So here's my source, here's my drain, here's my gate, and that makes the body of my material N-doped. What sign of voltage would I need to apply to my gate then? So if the body of this material is N-doped, what charge will build up in the N-doped material at the depletion zone? Positive, right? The opposite of what it kind of looks like here. So opposite of N. What do I have to apply to get rid of a positive charge? Negative. So then, in this case, my gate needs to apply a negative charge to get rid of these, and then I can get current to flow through. If you'd like to think about it more simply from it, if I have a p-doped body, P looks like positive, I have to apply a positive charge to the gate. If I have an N-doped body, N looks like negative, I need to apply a negative charge to the gate to get current to flow. Either way, they're the same idea from it. If I have an N channel from my body, I'm again applying a negative charge. I draw that as my arrow going this way from it. If I have a P channel, I'm applying a positive charge and pulling that electron away from that gate. So the arrow drawing for them in a circuit schematic looks different. This is my schematic, though, for a transistor. We saw them inside of an op-amp when I put a big circle there. You get a flat line that's really telling you the body of that transistor and where that gate will be applied. And they get a wire going off one side to the drain, one side to the source. That's where I'm trying to get current to flow from source to drain. Okay? But current will only flow based on what's applied at this third wire connection, which is my gate. Okay, we can watch this video. Again, I'm going to just forward to the part where we were talking about our transistor so we can make sure we understood how that part works.
Why? Because I filled the holes in the p-type. Now this makes the p-type negative thanks to the added electrons. And this is important because the p-type will now repel any electrons that try to come across in the n-type. So the depletion layer actually acts as a barrier, preventing the flow of electric current through the transistor. So right now the transistor is off. It's like an open switch. It's in a zero state. To turn it on, you have to apply a strong positive voltage to the gate. This attracts the electrons over and overcomes that repulsion from the depletion layer. It actually shrinks the depletion layer so that electrons can move through and form a conducting channel. So the transistor is now on. It's in the one state. This is remarkable Because just by exploiting the properties of a crystal, we've been able to create a switch that doesn't have any moving parts, that can be turned on and off very quickly just with a voltage. And most importantly, it can be made tiny. Transistors today are only about 22 nanometers wide, which means they're only about 50 atoms across. But to keep up with Moore's law, they're going to have to keep getting.
They've actually made them a lot smaller now. The newest ones is 3 nanometers across, which is very tiny.
Moore's law states that every 2 years, the number of transistors on a chip doubles. And here's the limit. As those terminals get closer and closer together, quantum effects become important, and electrons can actually tunnel from one side to the other. So you may not be able to make a barrier high enough to stop them from flowing. Now, this will be a real problem for the future of transistors, but we'll probably only face that another 10 years down the track. So
we face that now. That's basically the point for it. The video is a little old from it. So as I said, about the smallest transistors we got now actually 3 nanometers wide. Most of those were accomplished by, instead of having whole regions of N-doped, P-doped, and N-doped, they've actually been able to make materials where you're placing a single atom. So you could place a single phosphorus atom, for example, to be your gate and control that atom's charge by changing it from it. But that requires very careful printing. As he was mentioning quantum tunneling, again, if there's a very short distance between your charges, they will want to kind of jump from one to the other. It's the basic idea of that. And if you don't have a high enough distance to separate them, then you don't care about even those depletion zones to change. They'll just jump all the way through. They're getting a new form of transistors that people have been working on for a while, which are called quantum transistors, that instead of using these whole regions, they're using the quantum spin of atoms to determine whether they are off or on. So instead of having to dope them with regions, I can measure the spin. And if you talked about spin of valence electrons in physics, a little bit from that. We won't go into that much in this class, but anyway, I can measure that spin orientation, and as it switches and I can control that, I can use that as my off and on switch. Much faster and actually much smaller than that. So they've been able to put in like at least the beginning tests of quantum transistors from that. You can fit almost 1 billion transistors on a single salt crystal from that, which is pretty nuts. Anyway, okay. Questions on our transistors? Yeah. Okay, good. So something has to control it as a voltage, and that is the harder part to control of whether then I have a positive or a negative voltage from that. Normally, making a positive or negative voltage isn't that big of a thing. I can't even have it oscillate off and on, right? If I have a sine wave that's switching from positive to negative, or a square wave that goes from positive to negative signs from that. But a lot of the time, you will just have them designed, again, because in one switch, I'm only trying to have a positive. I can have that voltage applied just off and on. And it's only going to be a positive voltage ever applied to it. And that would make a current flow through when it's applied. And when that's not applied, I don't get anything from it. That is the harder part for doing that versus the rest of the design. You've got to still somehow control that voltage at the gate to be positive or negative. But because it will respond so quickly the second it is that charge, it still works pretty well. So how that works into a computer gets us into our next one. I'll actually jump ahead and answer that question. Sorry, hold on. Oh, I didn't. Where did I put that? Hold on. Oh, we talked about that when we do light ones. The biggest way that it interacts with the computer, but we will talk about that later, again from it, is that each off and on is going to represent a bit. So each transistor that I can measure whether it's current or not, I can have represent as a bit, as a 0 or a 1 from that. And so I need basically the number of transistors that I need bits for to store something. So when it's off, I'm going to call that a 0, and when it's on, I can measure that as a 1. And that's normally how our computers then count. But again, something had to apply that voltage to them to make them do that from it. And we will talk more about that when we get to measuring light, actually. There are two different designs that are common for our base field effect transistors. One is a JFET or a junction FET, which means that my gate is actually touching or pretty close to touching the body of my transistor. The other one, which is a little more common but slightly more expensive than that, is a metal oxide FET, where my gate isn't actually touching here because I don't really want my current to go from here to my gate. I want it to go from my source to my drain. So I put a little barrier here that is an oxide layer. Remember we talked about the difference between silicon and silica is whether it has oxygen on it. That oxygen is pretty insulative to wanting current to flow through it versus our base forms from it. And so if I have an oxide layer, that acts like a pretty good insulating barrier. I can still detect that charge, so it still helps overcome the negative charges that would build up, in this case in my P-type, and allow current to flow, but it won't allow current to flow this way from it. It just helps overcome that negative charge on the body of my resistor. That's what's called a MOSFET, so it's a metal oxide barrier at the gate. A junction FET will have a line in its circuit schematic that goes directly to the gate, or sometimes with a little gap between that. But my metal oxide FET has this kind of dashed line before I have my gate, indicating that there's an insulating barrier there. Our transistors, in addition to being a switch, they're also what allow our op-amps to amplify or to increase current from it. So a buildup of charge, even if I have a really high voltage here, I have 5 volts, 0 volts here, I would normally want current to flow from 5 to 0 volts, from my higher voltage to lower voltage, but it will not flow again unless there is a charge applied to my gate. So that small gate, once that's applied though, I do get current to flow like crazy, and I can actually amplify that current. Why? Because it's not just the voltage difference between here and here. I now have extra, in the case of my N-type material, I have extra electrons from here. They want to move into my P-type, and from my P-type over into this N-type. So the actually body of your transistor can provide more charges to amplify current than what you just had from your voltage across them or not. So it acts as, again, an off or on, or like a binary, 0 being off, 1 being on. But I can amplify that current in the process. Our diodes are a little simpler than our transistors. They don't really act as a switch, but still when I get those two regions that build up, again, I get my depletion region here. What's special about them is, again, like our transistor, they will only allow current to flow when a certain voltage is applied. Now, they don't have a gate to apply that voltage. They just have their two connections. So, for example, if I apply 5 volts here compared to 0 volts here, again, in my depletion region, what sign did I say would build up on the P-type material in the depletion zone? Negative. Over here, that means I'm left with positive. So if this is positive 5 volts, it'll overcome that negative charge. Or if this one was negative compared to that, it overcomes this. And now I get current to flow through it. But it's just based on what charge is applied to the ends, my N-type and my P-type material. There's no gate for those. Our diodes, because then they only allow current to flow in this one direction, are normally written in a circuit schematic by an arrow indicating the direction of current flow, and a line from that. If you're getting a diode in lab, which we will use diodes in our pulse sensors in our next lab from them, they look a little bit like resistors, quite frankly. They kind of look like little cylindrical rods for most of it. They're not as bulby shaped, and they only have one band instead of having 3 bands on the resistor. But that band is marking the direction for current to flow. So you want current to flow from positive to that band. Because then that band is the cathode, or what should be attached to your negative charge from it. Your anode, kind of like its default negatively charged, should be attached to your positive charge from it. Okay. So what happens when I connect my diode with different voltages across it? So if I apply a positive voltage to my P-type material, and then the negative voltage compared to that to my N-type material, what do I think will happen? Do I think positive current will flow from my P to my N-type, positive current will flow to my N to my P-type, or I will not have any flow whatsoever? You can talk to your neighbor, see what you think. Okay, how many people say C, no flow, when I attach positive and negative? Few, okay. How many people say B, positive current will flow from my N-type to my P-type? Okay. How many people say A, positive current will flow from that? Okay, that is correct. We define positive current. Remember, positive current was discovered before people knew that electrons were what moved, and they like to be optimists and they assume positive charges move. When I have a positive 5-volt source, right, and you apply it to a resistor, ground, which way do we say current is flowing from it? If this is positive compared to negative, we always supply our current from positive charge to negative. Now, we know now that it's really electrons moving in the reverse direction, so it's a little weird to think about, but we still always define it from positive to negative. If I apply a positive voltage here, again, because those negative charges will build up in my P-type at the depletion zone, they will be counteracted by that positive charge, and they'll go away. Similarly, the positive charges here will be counteracted by this negative charge, and they'll go away. And now I can allow current to flow just like it was a set 5-volt difference across. The positive direction of that current, we always say, goes from positive charge to negative charge, even though in reality that means electrons are moving the reverse direction. So my positive current will flow from my P-type to my N-type. What happens when I do the reverse? So what happens when I connect my diode with a negative voltage to my P-type, positive voltage to my N-type? Same options, but what do we think will happen? Okay, how many people say C, no flow? Okay, how many people say B, positive current from N to P? How many people say A, are still positive current? Now, a lot of people did not vote. Okay, for those of you who said no flow, why? Yeah, they won't get canceled out. In fact, they'll just get worse, right? If I have positive charges here on my N-type material at the depletion zone, and I apply a positive charge, it's just going to build up more positive charges on this side. It actually makes your depletion region grow. So now it's going to be a larger area and more charges. Similarly, with the negative charges build up on my P-type, I attach a negative charge to it. Now you just got more negative charges there. If my depletion zone grows, that's a bigger barrier for current to want to flow from it. So in general, current will not flow if you hook up a diode in the wrong direction. This will be important when we're in lab later, and you need to pay attention to which direction your diode goes. We haven't cared about directions we hook up things like resistors or our capacitors before, but our diodes do matter from that direction. So will our transistors from it. So I will not get flow. As if I'm trying to flow from positive to negative, this is now a big barrier for that, and I'm not going to get anything across it. Now, barriers are only good up to an extent, right? We talked about even capacitors that are supposed to separate a charge under DC and not allow any current to flow. Under DC, if you apply a very high voltage difference, positive 1,000,000 volts to 0 volts across a tiny capacitor, it will still jump that, even though that's an insulating material between that. That's a principle between lightning and static charges. The same thing will happen here. For most voltages that are positive applied to my N-type and negative applied to my P-type, current won't flow. But if I made this something probably like positive 100 volts compared to 0 volts. That's a big driving force, and it will even jump over that if that's enough. But for most things, it won't. What does that mean? So my depletion zone is going to grow from it. It means when I hook up my diode, I have a different impedance, or again, my resistance to electrical flow, in one direction than the other. So I have a low impedance in one direction. This is what's called my forward bias, to get current to go in the forward direction. And I have a high impedance in my other direction. Again, for most of it, it's not going to allow current to flow unless I got a really big voltage difference. That's what's called my reverse bias. And again, it's all because of that depletion zone and what charges build up there. If I make that depletion zone grow even larger, that's going to be more of an impediment. If I can make that depletion zone get smaller or go away, then I get less impedance from it. The forward bias is what's also called the voltage drop required to eliminate the depletion zone and allow current to flow. So again, if I apply something, this side is positive, right? The longer wire always means positive from this, compared to negative, and I apply positive to this P, then where I had my depletion region, it will start to decrease. If I apply even higher voltage, so from 0.4 to 0.7 volts, I might get that depletion region to go away entirely. And now I get current to flow from this. If I apply them in the wrong direction, though, positive charge to N, negative charge to P, my depletion region just gets even larger, in which case I don't get current to flow from that. There is a set amount of voltage, though, so 0.4 volts here, I still had some depletion region because it wasn't enough charge to get rid of what naturally moved from one side to the other. 0.7 volts was enough. Each diode, based on what materials they're used for it and their doping, has a certain forward bias voltage. What voltage you must apply to get current to flow in that direction. For silicon diodes, which are what we use in this class and are pretty common, they have a forward bias voltage drop of 0.7 volts, which means as long as I apply 0.7 volts or anything above that, they'll allow current from positive, negative in that direction. If I apply only 0.4, though, they still probably won't allow current, or at least not much. If I hook them up in the reverse direction, not anything from it. It is based on the material, because how much of those charges are going to move is based on what I dope it with and what its base material is. There are other semiconductor materials, germanium being one of them. They have a different voltage drop, so around 0.3 volts. Okay. Elijah, do you have a question? Mm-hmm. So if I increase this because I applied positive to this side and negative to this side, and then if I flip the voltage that I apply to this, yeah, it will change pretty quickly. Like if I apply something different to that, they will go back to it. This was only building up because I had an applied positive voltage here. The second you detach a diode from its voltage, it's going to build up its only natural length of the depletion region. Because charges want to move back based on diffusion from that. So it's a... Good question, though. What does this look like in a graph? This means my diodes are pretty weird when it comes to voltage and current. We have been used to our favorite equation, V equals IR, but again, that really only works when they're resistors. We had a kind of shortcut for that we could say V equals IZ and do impedance if we had something like a capacitor or an inductor. Diodes aren't any of those. We're not going to have a set impedance. We're not going to have a set resistance. They are their own weird animal of electric elements. They do not behave that as current increases, voltage would increase as well. They don't have that necessarily role. In forward bias, as in I apply a positive 0.7 voltage from my P-type to my N-type. Once I get to 0.7 volts, what happens with my current here? It goes up exponentially. And in theory, I could almost have infinite current go across that diode, and I will still only have a 0.7 volt voltage drop across it. It will not increase voltage with current, unlike our resistor. In reverse, so I apply negative voltages, right? My x-axis here is voltage. If I'm applying negative voltage up to something, still very little current, or practically nothing, until I get to something high enough that it will even overcome that bigger depletion zone and is enough of a driving force. And then I do get current, negative current, because it's in the reverse direction. And this is what's called a breakdown. It's a reverse bias breakdown. So again, I'm trying not to allow any current through there, but up to some point you will if you apply a large enough driving force. What's cool about this, although it's annoying for us to get our heads around since we're used to voltage and current changing fairly proportionately, is that no matter what current I apply to my diode in forward voltage, I have a pretty constant voltage drop. Again, that 0.7 volts, even if I apply 10 milliamps, even if I apply 100 milliamps from that. What's nice about that is you can use it as a voltage reference. A lot of our other things change voltage slightly based on what current. We've even had to be careful of how much current we're trying to draw out of our batteries and our power sources because they can't supply that voltage with that much current. Diodes will keep this pretty nice voltage reference of 0.7 volts fairly constant because of that. Questions or concerns about that? Okay. It's very similar, although the values are different from that, with our transistors. Again, I get a source connection, a drain, and in the middle I get my gate. In theory, we said if this was N-doped, P-doped, and N-doped, my type, that I needed to apply a positive voltage to my gate to, again, overcome those negative charges that would build up in my depletion zone of that body. That positive charge has to be high enough to overcome that depletion zone. How high is high enough? It's based on what material you use for your transistor. So again, it might be 0.7 volts, it might be 1.3. Normally, it's pretty low in terms of a voltage from it. But once I get that voltage, even if I apply higher voltages, I can get whatever current going through there, and I can amplify that current now from source to drain. Okay. That's when it's talking about our diodes and our transistors, although we will start talking about them now in terms of them using them as sensors. So we'll get into this a little bit. Now I'm going to be talking about measuring things that aren't electric to begin with. So we've talked about how to measure voltage now, how to measure resistance, how to measure current, how to measure capacitance, and then we've gotten into weird electric elements that are our diodes and our transistors that can help with that. We're now going to measure things that are some energy form that isn't electric to begin with, but we want to convert to an electric form. So for example, light or heat or mechanical things, we're going to talk about position, velocity, and acceleration. We'll start with light. So light, we can talk about both creating light and trying to measure light. Our common ways of creating light are going to be LEDs. What is an LED? Light emitting diode. The diode part of that is what we just learned. They are a semiconductor material with one region N-doped, one region P-doped. Okay? We'll also talk about photomultipliers from that. And then the ways we can measure light are using phototransistors, photodiodes, which are different than LEDs. They measure light, not create it, spectrophotometry, and fluorescence. So in creating light, we just said what an LED was, a light-emitting diode. What light they emit, what wavelength of light or color of light, is dependent upon what's called the band gap of their semiconductor, i.e. what energy is required to release a valence electron to become a conduction electron. So again, all atoms have their valence electrons they like to keep in their orbit and shell. If you're going to free one to move across our diode or across our transistors or just into a current from it, you are freeing it up to what's called a conduction electron. It is now free to move or conduct current from it. I can change what color light I get from an LED by choosing what semiconductor materials and what doping I put into that, because it will change what energy then is needed to move those electrons. So for example, gallium phosphorus from it is an LED that will glow electroluminescent at about 700 nanometers from it. Anyone know what color that is? Red. If I have gallium, silicon, but now I do sulfur with it, with silicon doping, with Si doping, It's at 540 nanometers. Anyone know what color that is? Green. Oh, we're good with our colors. Okay. The green is actually helped a little bit, kind of in a fake version, by having a phosphorus coating. We'll talk about that, but it's a light going to hit the coating and makes it release at a slightly different wavelength. If I have gallium nitride or indium gallium nitride, these are a lot of the elements that you don't think about probably on a day-to-day basis, but they're very useful in semiconductor materials where they come out of the woodwork. They have interesting properties from it. I can get blue light. In general, they've been better about that in recent years, but a blue LED is the most expensive LED you can buy because of those materials to make that and that doping. Again, just requires what energy would it take to free that electron from those atoms. So changing the material, I can change the light from that. Red is pretty cheap and green based on that too, but reds are one of the common ones. We will be using red LEDs next week in lab when we're doing part of our breathing sensors. So you'll be lighting up an LED each time you breathe, or we'll talk about lighting up a virtual LED, but it'll be the same idea. When you haven't breathed in a while, that might indicate your patient is dead. Okay. Questions or concerns? Any of that? Hey, have a good one. Oh, you will have a homework. Your homework number 3 will be posted today. It is due next Wednesday. And again, no class next Friday. I'll post the things about going to capstone presentations if you want to do that. Yes. Okay. Yep, I'll be in there again like 1:30 until 11, 3:30 o'clock.
So test 2. Is there any way I can make one up or do something?
Yeah. Just let me know when it's closer to time for that. So I have when you want to see it.
Cool. I'll just get.
Yep. Questions over here. Okay. If you have time right now.